In today's lesson, we are going to be looking at continuous versus discrete data. We've looked a little bit at this before when we've looked at discrete probability distributions, but we're going to be looking again just at the difference between the two, and then we're going to focus on continuous distributions. So just to kind of get you thinking, when a company fills an aluminum can with pop for sale, they print the milliliters on the can. Often the can is set up to fill up 355 milliliters. What is the probability that a pop can, which has been filled with 355 milliliters of liquid and advertises 355 milliliters, actually contains the 355 milliliters? So just kind of think about this, thinking about the probability that when a can is set to be filled up to a certain amount and is advertised at that amount, what is the probability, or what do you think the probability might be that it actually contains that amount of liquid? And the idea that we're getting at here is that we're looking at, rather than specific or set values, we're looking at a measurement. And with a measurement, to contain exactly the amount, to get to that exact amount, you'd have to have a very, very, very fine-tuned machine to get to exactly 355.0 milliliters. When we're dealing with continuous values or data, it's going to be very difficult to get to an exact value because we're dealing with a range. So this is going to get into our look at the difference between discrete and continuous. So continuous data is obtained by measuring. So whenever we're measuring something, that's going to be a continuous or continuous data. And again, it doesn't mean like if we're just counting things, when we're actually measuring or timing something. So there's basically what this means is, though, there is always a data point that can exist between two data points. So for example, if I'm given 2.5 and 2.75, there's a possibility that I could get a data point that falls in between. If I'm measuring something between 2.5 and 2.75 pounds, there's a measurement in between that, 2.6 pounds, right? Or there's 2.55, 2.05, 2.00, 2.500006, something like that. There's always a data point that can exist between two data points that you have. And this basically gives us a possibility for infinite data points, or an infinite number of data points. And when we have continuous data, we organize it into intervals. When we're dealing with discrete data, which we have been so far in the past, especially with probability, discrete data is obtained by counting, right? And we've done a lot of counting in this course so far, right? We've looked at different ways to count, especially when finding probability. And here, when we have discrete data, we have a finite number of data points. So there's only specific data points that we could have. And we do not have points between points. So an example of this might be looking at the number of siblings an individual has, right? It's a set number, and I can count it, right? So there's one sibling, two siblings, three siblings. I'm never going to have to worry about, well, what if I find an individual that has 2.5 siblings or 2.07 siblings, right? There's never going to be a value in between those. So that's what we mean by there's not a point that can exist between two of the points you have. And again, if you have to think about it, if you've measured something, that's continuous. If you're just counting, that's discrete. When we've dealt with calculating probabilities, especially for discrete probabilities, we've determined it by counting the number of successful outcomes divided by the total number of possible outcomes. And in a discrete probability histogram, as we've seen here, and we've done these before, each outcome has its own probability, right? So if this was, say, flipping a coin, and we wanted to see, okay, what's the probability of getting, flipping a coin 3 times, what's the probability of getting 3 heads, or 2 heads, 1 tail, 2 tails, 1 head, or all tails, we might get something like this. Right? So we have an individual probability for each outcome. When we're dealing with continuous probabilities, it's going to be a little bit different because we don't have a fixed value. So when we're dealing with continuous probabilities, we determine, or we find the probability by finding the area under the graph between the intervals. So basically similar to what we did, except instead of counting it, we're looking for the area under the graph between the intervals. And the nice thing is that the area of the bars under the graph adds to 1 or 100%. And we're going to look specifically in this lesson at uniform distribution because it's very easy to see that. So if I look at example 1, given our probability distribution histogram of wait times for a subway train that comes every 10 minutes, A, what is the probability that a wait time will be between 2 and 5 minutes? So if I look at my probability distribution histogram here, I have the wait times anywhere from 0 to 10 minutes. My bars are intervals, so it ranges anywhere from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 6 to 7, 7 to 8, 8 to 9, and 9 to 10. Right? They're arranged into intervals because when I'm recording time or measuring time, I can have an infinite number of possible times. Right? Again, depending on how finely tuned our recording device is or our stopwatch, we could time it down to, or we could get an infinite number of times. And it's a uniform distribution, so we can see that by the bar or each bar having the same height. Right? We can see that kind of box shape that we've talked about before. And we can see specifically what probability is for each bar or for every interval. And here we can see that it's 0.1 or 10%. So what is the probability that a wait time will be between 2 and 5 minutes? So if I want to think about the area underneath my line between 2 and 5 minutes, I could think of it as, well, how many possible or how many intervals do I have there? Or I'm ranging from 2 to 5. Or if I wanted to find the area, the difference between 2 to 5, or 5 minus 2, will be the one dimension. And I'm going to multiply it by the height, which in this case is 0.1. So I get 3 times 0.1, or 0.3. Or basically, therefore, there's a 30% chance of the wait time being between 2 and 5 minutes. What is the probability that our wait time will be more than 6 minutes? So that means from 6 minutes up to 10 minutes. So here we're going to find the area again, but for a different section, everywhere from 6 to 10. So here our area, or our probability of 6 to 10 minutes, is going to equal the base, so 10 minus 6, times the height, which is the probability, so 4 times 0.1, which equals 0.4, or 40%. So there's a 40% chance that our wait time is greater than 6 minutes. C, what is the probability that the wait time is less than 2.5 minutes? So we can't really see 2.5, but if I was to make a mark at roughly 2.5, and I wanted to find the area again underneath my line, the probability of it being less than 2.5 is going to equal, again, because I'm finding the area of the bars that represent this. We have 2.5 minus 0 for our width, you could say, and then multiply by 0.1 for our length or our height. We get 2.5 times 0.1, which is equal to 0.25, or 25%. So there's a 25% chance that the wait time is less than 2.5 minutes. Finally, for D, what is the probability that a wait time is exactly 4 minutes? Well, in this case, if I look at exactly 4, exactly at this value, so the probability being 4 minutes exactly, well, my base or the length or width, you could say, again, whatever measurement of the interval, so 4 minus 4, so I don't really have a width, multiplied by 0.1, 0 times 0.1 equals 0, or 0%. And this does kind of make sense, because if you were to think about it, in order to get an exact value, an exact single value in an infinite number of possible outcomes between 0 and 10. And again, if we go down to the very smallest decimal place, maybe you can't even think of the decimal place, the probability that it's going to be exactly 4.000000000, infinite number of zeros. The probability it's going to be exactly that value is 0%. If you want to time it down, sure, maybe to the seconds, but if you look even further past that, there's probably milliseconds, nanoseconds, microseconds. I don't even know the rest of the units for smaller seconds, but you're never going to get exactly 4 minutes. So when we're looking for an exact value or an exact continuous value in uniform or in continuous probability, you're never going to find it. Or the probability you're going to find it is going to be 0 or pretty much 0. Just because there's that infinite possible number of outcomes. Example 2. The Allenberg Bridge takes 20 minutes to raise and lower. Assuming the wait times form a uniform distribution, construct a probability histogram for this distribution. So if I wanted to come up with a probability histogram, I see that I'm going from 0 to 20. Right? I have intervals of 5. I'm not too worried about what the intervals are. I need to figure out what is the probability. Well, because I know that it's uniform distribution, then I know that it has to be the entire height has to be uniform across, and I know that it has to equal 1. I know the probability has to add up to 1. I have at least an interval of entire thing of 20, because I know it has to go from 0 to 20. So the way I can figure this out is that I can figure out the probability is equal to 1 divided by 20 minus 0. Or in other words, I know that if I find my area, which is length times width, I know the area has to be 1. I know the width, or the length, we could say, is going to be 20 minus 0 for the entire thing, times the width. We get 1 divided by 20. Or, well, now we're at this step here. This works out to 1 over 20, or 0.05. So our graph is a little bit smaller, but again, we know that our line couldn't be higher than 1. At the most, it has to be 1%. So let's say at about 5, let's say that's our line there. We can draw our lines down for our intervals. So 0.05, or basically 5%. So there's a 5% chance for each interval, or for every grouping of 5 minutes, you could say. So B, what is the probability that you'll have a wait time between 5 and 10 minutes? So I'm going to draw my graph again here just so I have the same values. Here we have 0.05, and I'm looking for specifically 5 to 10 minutes. So I'm looking for the area of this bar, or this section of my histogram. In this case, probability, the x is between 5 and 10, is going to equal the area of this. So in this case, it is 10 minus 5 times 0.05. We get 5 times 0.05. Which gives me 0.25, which does make sense because this is basically 1/4 of our entire thing, which makes sense that there's a 25% chance that we'll be waiting between 5 and 10 minutes. Good. All right, some of the challenges when dealing with continuous variables. Sometimes whatever we're dealing with, whatever our intervals tend to be, they're not always going to be intervals with a width of 1, or they're not always going to start at 0. And if that's the case, then we need to convert the intervals so they are equal to a 1 unit, or 1 unit in width. And this is more for when we're already given a table. If you were to try to find the overall probability of this graph, right, so if we were to find probability of the entire graph, we would do 60 minus 25 times, say, roughly 1.4. I'm sorry, 0.14. And we get 4.9. Clearly that doesn't work because we know that the total probability has to be 1. So when we convert our intervals so that we start at 0 and we use units of 1, still recognizing that this still represents 25 to 30, 30 to 35, 40, 45, 50, 55, 60. Still recognizing that that's what those values represent, but we're using different numbers or different scales that allows us to calculate the probability. Because now when I do it, 7 minus 0 multiplied by 0.14, 7 times 0.14, I get 0.98, but again, it's slightly above, so we can argue that this actually does work out to 1 or 100%. So again, that's the reason why if our interval doesn't always start at 1 or they're not a width of 1, it does help that we start or have our interval set up. Or we change the values, sorry, so that our intervals have an equal or a width of 1. Some other challenges, dealing with less than or equal to. So when we're dealing with these terms, you might think about, okay, well, what's the difference? Right? We do know that when we're dealing with discrete values, there is a difference of what we have to actually calculate. However, because when we've looked at in a previous example, that when you're trying to find the probability of an exact value, the probability of it being an exact value is 0%. So therefore, when we say that something is less than a value, that's the same as saying it's less than or equal to that value. So you don't have to worry, or you don't have to try to get confused about including it or not including it. It means the same thing when we're dealing with continuous variables. So if I said find the probability of it being less than 2, or sorry, less than 5 minutes, let's say, that's the same as saying what's the probability of it being less than or equal to 5. So still the same, where they basically mean the same thing, because the probability of it being an exact value is 0. So in this lesson, the main thing was just, again, understanding that when we're dealing with continuous variables, we're going to be looking at probability distribution histograms where we're dealing with intervals and we need to find the area underneath, or the area of the bars, in order to calculate the probability for that interval. We've looked at different examples of that. We've looked at some of the scenarios that have come up where we might have to change some things for when we kind of, again, come across those scenarios.